we go. Okay, so we got voice, we got image. Okay, we are all ready to roll. All right, so I'm going to go to my homework assignment, and I'll do exactly the same thing that you guys will have to do. And
In far, far less time. In far, far less time.
well, we'll see. I have slightly more than an hour
Oh,
from
I have
now.
one question though. When you're zipping, you're tarring a file, what does the left apostrophe PWD
Oh, yeah, yeah.
left
Go
apostrophe do?
Oh, that just shows your current. It's print working directory (pwd), so it prints the full path to your working directory. Okay,
And then
first-
when I tried looking there and then in the folder behind it, but it actually writes to the main folder, like all the way back in.
That's what the tilde does.
Okay,
That's
what
what-
tilde does.
Yeah.
Yep. All right.
And then the capital C.
The capital C
Dash
is.
capital C.
Yeah, dash
It
capital C.
changes the folder from which point the command is actually run.
Okay, because when I ran it the first time and I didn't know that the quotes were the other way, so it didn't work. And then I tried running with a lowercase c, thinking that was maybe a typo, and it just ran like it wouldn't stop. It got caught in a loop, and I had to shut down the window.
Okay. All right, so I'm almost there. Okay, I am there, but I did tell you guys to use the new updated makefile, so I'm gonna overwrite that one using the one from the news forum. So new and improved makefile. Right-click on this one, save link as, and I can just overwrite the other one, like this one. Save, yes, overwrite, replace, and we're good. Okay, so now we can actually get started. And I'll maximize this screen. Can people in the back see okay? Okay, all right. And I'm gonna do the auto setup just to be sure that, you know, the, okay, yep, sometimes it loses the one side or another. Okay, so we'll go ahead and get started with atof.c. Okay, that's the program that we're dealing with. And we'll be doing a lot of coding down here, okay? And I'm going to do this the first time also, okay? So it's not like I have a big, huge rehearsal at home and have the whole program memorized. Which would make it not so much fun. See, I really like writing programs myself. Okay, so the focus is the syntax first. Okay, so the syntax says, you know, you can have an optional sign which can be plus or minus, but that's optional. You may or may not have those signs. A single digit, a period, and that period is optional. But if you have that period, you can also have optional decimal places after the decimal point. And then after that, we have an optional exponent. And then within, if you have e, then you can have an optional sign, okay, for the exponent, which can be plus or minus. And then you have, if you have e, you must have at least one digit, okay, because the plus means at least one. Okay, so that's the basic syntax of, you know, what you need to parse. So I will start with the parsing part, and we'll get to at least the numerator divided by the denominator. Okay, so that's what we want to do. Okay, so here's the source code, and I think I can still remember the syntax in case I do not. Okay, so I'm just going to copy this and paste it here as comment, just to remind myself, you know, what I need to do to parse it. Okay, which comes in handy. All right. So here's a string pointed to by ptr, which is basically an array of characters. And the way you parse this is to look at the characters one by one. I did not tell you guys that you have to, you know, get past like white space and stuff like that. So you can't assume the number just starts right away. Okay. And the first thing we will do is to be optimistic and say, well, do we see a digit? Okay, because, you know, if that is the case, then I don't have to do any special parsing. And to do that, I have my other subroutine that I talked about the other day, which is, you know, parse decimal, okay, and it requires a pointer to an integer, which is the result, and also the string itself to be parsed. So this is const char ptr that. Okay, and the way this works is I am going to interpret the result or what I'm seeing in the string, and I'm hopeful that this is an actual number. So I need another integer to store the result. Okay, so here's the result, which is initialized to 0. And all I need to do is to say, as long as PTR is pointing to something that is greater than or equal to the ASCII code of 0, and it is also, whatever it points to is less than or equal to the ASCII code of 9, then I'm good. I should stay in this loop. In this loop, the first thing I do is to increment PTR, so I am now pointing to the next character. And then the other thing I have to do is to say result gets result times 10 plus the difference between whatever, I have to put this the other way around because I need to use whatever PTR points to first. So I will subtract the ASCII code of 0 from whatever PTR points to. So that will give me the value represented by that digit. Because the digit, remember, the digit 0 has an ASCII code of 32 in decimal. Okay, so I have to subtract that, to get the offset. This is code that I have given you already, so there's nothing new here. Okay. I also need to have a counter, so I'm going to put a counter here, which is also starting with 0, and we just add 1 to the counter every time we process a character. When we're all done here, then we'll go ahead. Result is not exactly required, but I kind of like to have it here because now I can say, if counter is non-zero, then I will go ahead and update whatever p result points to be the same as the current result, and I return the number of bytes that I have processed, which is tracked by counter. So I think this code is already disclosed, and you guys were informed that you can use it if you want to. How many people made use of something like that? You might have made like slight changes to it or whatever. Okay, so this is really helpful because the first thing I do is to be optimistic and say, let's see if we actually got a number. Okay, but the important part is you have to remember the return value of parse dec because that is really, really useful. So what I'll do is I'm gonna say, okay, we'll have another integer here. The size is not really important because we're only dealing with a small number here. So we'll say int I'm going to put it inside the local block so I can reuse these names here. So I'm just going to call I just call it counter. Okay, and counter is parse dec, and I need to store the value as well. So here's the actual result. We'll pass PTR as PTR, and we'll pass the address of result as p result. When it comes back, I want to take a look at counter and say, okay, did we parse anything, right? So if counter, if not counter, then what does it mean? If counter is not 0, okay, not counter is the same thing as confirming that counter is 0. So if counter is 0, that means I did not get a digit. But that's okay because it can be a plus sign or a negative sign here. Okay, so now I check for the actual signs. So if counter is 0, then I know, I leave a little note to myself, and also up here I'm going to say int 64-_t, and this is just to keep track of the sign. Okay. So here I use comment to remind myself what I'm dealing with here. So I'm just going to say parse the sign because it has to be the sign in this case. So I can, with this one, since I told you that I would not give you something that's erroneous, you can just basically say, it has to be one or the other. Okay. So if pointer, whatever pointer points to is the plus symbol, then I don't have to do anything because I am going to initialize sign to 0. On the other hand, if it is negative, that's the only time I actually have to do something about it. And what I will do in this case is to say sign equals to 1 shifted to the left by 60 3 times. Because it is a mask that I will use later on to do the bitwise OR with everything else. Okay.
So we were to actually look for a plus.
I don't have to
just be imply when it's
in an actual program. Yes, you would probably want to confirm it is a plus if it is not a minus sign because you want to do error checking. But in this assignment, since I told you that you will not be given a incorrect input, so you don't really have to check what the other one is because it has to be a plus sign. Okay, but just to show you what I mean by that. So technically speaking, you probably should do something like this, okay? And just do nothing in this case because there really is nothing to do. And just do an else here. And if you have any type of error reporting facility or ability, this is where you want to do it, report error. Because it is supposed to be plus, minus, or a digit. And we are not seeing any one of those 3. Okay? All right. Are there any questions about this logic up to this point? Now, the other thing that I really should do is, if I confirm it is a negative sign or a positive sign, I should increment a pointer, PTR, so that I can move on to the next character to process. So I would just go ahead and do it. So let's go ahead and do that here, plus PTR, and just plus PTR here. All right. So I'm now done with, almost done with the first digit, not quite, okay? Because up to this point, okay, I'm still inside this condition, which means I did not actually parse a digit. So if I do it now, so I can do it now and expect exactly 1 digit, okay? Because I told you that the first digit is going to be just 1. There won't be any multiple digit here. So I would have to do it again, and I'm going to say counter is parse dec PTR ampersand result here. So I'm going to reattempt to parse a single number. If you want to check for error, this is a good time to report an error because it has to be a digit at this time. But if it's not, then we have a problem. Yep.
Since it was only going to be 1 digit before the decimal point, wouldn't you not encounter a digit right here? Would you have to increment it 1 more time to get to more digits?
No, because this one is if I did not encounter anything before. It's still inside the conditional statement.
Right. Oh, I see.
So at this point, we have just processed the sign, but not quite the digit itself.
Gotcha.
And this is why this program is going to be kind of long because so I want to use local blocks just to be clear. Like this chunk of code is only dealing with this part of the number. All right. So if it is not if counter is 0, I have a problem. But let's hope that it is non-zero. Then I can do something about it. So I would use another local variable here, int 64_t, and this is going to be my numerator, okay? So I'm just going to use num here to indicate this is my numerator, initialize it to 0. And right here, I'm going to say my numerator equals to result. And there's one more thing to do because I have to increment the pointer by the same number of digits that it has processed. Now we know this has to be 1, okay? But that means counter has to be 1 in this case. So I'm going to just say PTR plus equal to counter. Is that okay? Now what about the else part of this? If not counter. The else part of if not counter is the first time we try to find a digit, we found one already. So that means I can just go ahead and repeat these these instructions here, and just say that okay, num is result, and let's increment the pointer by the same number of characters. So now we should be on a period, or there can be nothing. Okay, because I can be done at this point. Are we still doing okay so far? So what you want to do is to stop here and then test your program, just to be sure that it is correct up to this point. Okay, so I'm going to show you what I mean by that. Just give me a moment here. There's a return X here. I can put a breakpoint on line 65 just to check the program up to this point. So I'm going to save it, go to main.c, and for the purpose of testing, I'm just going to give it a simple test case. Okay, so I'm going to try one first. Okay, because it is simple. Then I can try +1 and then -1. Okay, just to be sure that it does work in all cases. So we can just go ahead and do it like this, plus, negative. So as it stands right now, it should be able to process every single one of these. And just so that we don't get accidentally get a result of 1, just because, let's change it to 7, 6, and 5. So it is unlikely that I would randomly get these values by the time I get to the end of that subroutine. Okay. So save the program. Oops. Exit. Make. And it complains. Oh, these are just warnings, so we are still good. GDB main, and we'll put the breakpoint in the subroutine ATOF. If you don't really care about the line number and you just want to stop on the first line of ATOF, you can just say B ATOF, break in the subroutine ATOF, and it will stop as soon as it gets into the subroutine. So I'm going to run the program at this point. It is now in ATOF just to process a single character 7. So I'm going to single step. I'm going to parse deck, go into the parse deck subroutine. It has 1 digit to process, and now I'm on the null terminator. And get out of the loop because it is no longer a digit. The pointer is no longer pointing to a digit. Counter should be 1 at this point, so it would change result or whatever P result points to the actual result and return the number of bytes that it has processed.
Can you display what's in the counter?
Huh?
What's the number in the counter? Is that
1. Should be 1.
Can you try?
So if counter is 1, then not counter is going to be false. So we go to the else branch, and in the else branch we just say the numerator is the result, which is 1, and PTR is we're adding 1 to counter, so it becomes the null terminator. It points to the null terminator, and we're done. Now X is meaningless because I did not do a single thing about X, so it would just be returning some garbage, which is okay because that's not the point of what I'm trying to make here. Then I'll just go ahead and continue execution until the second call is stopped by the breakpoint. But this time it is what, +6. Okay, I can see that. The debugger is kind enough not only to show me where pointer is pointing to, but also the content, assuming it is a string that is null terminated. If it is not null terminated, it will just give you some gibberish after the actual useful content. So I can do the same thing here, just keep single stepping it, and then we are now back to ATOF itself, and it is a plus sign, so it goes to line 40, which is the then branch corresponding when the sign is plus, and now it will call parse deck again because the first time it called it did not actually process any number. This is the second time, and it will return a 6 in P result, and counter should be 1 in this case. Yep.
You checked for the negative, but you don't store that you encountered a negative.
I did. Yep, I did. You will see the third test case will confirm that. So return counter back to ATOF. Counter is actually 1 in this case, so not counter is false. We get to the else branch. Num should be 6 in this case, so we'll print num. It is 6. We'll print sign. It should be 0. Yep, and we're all done. This is the third time. Okay, the third time has -5. Okay, so we'll confirm whether we actually process the negative sign or not. Okay, so single step. The first time we call parse deck is not going to process anything because it's the negative sign. So counter is 0, not 0 is true. We go to line 33, and then it will say, is it a negative sign? Yes, it is. And this is how we remember.
Oh, it skipped over the. Okay.
Yep, it just Yeah, it stores the entire bit mask. So later on, I can just do one single OR with everything else.
When you were stepping through, I forgot that it's not showing every step. It's just going every step it's processing.
Right. And that's why some people do not like GDB, because it doesn't give you the actual list of source code. So single step, single step, single step, single step. This is the actual digit that is processing, which is 5. And when we get back, counter is 1, not 1 is 0. And it goes to the else branch, and num should be 5 in this case.
Can you display without?
So num is 5, sign is A.
At least 1, change it to 0.
Okay, I made that little mistake. I mentioned it in class, and then I myself forgot about it. Because I have to cast that 1 to unsigned long, so it becomes 32-bit. Otherwise, everything will be shifted out of a 32-bit number. That's why it didn't work. Okay, but it's there. The code is there. It's just that I did not use the right type. So good thing I checked my own program at this point, right? If I had waited and say, this is going to be okay, and I would keep writing the code, then by the end of the whole thing, the program doesn't work, and it would be much more difficult to find out why it's not working, because the program would be much longer at that point. Okay. So as I said, in class, this is going to be an entertaining process, because you get to see all the errors that I will make when I write programs. There we go. That should fix it. Okay. So let's go ahead and test it again. Okay, because just because I said it's fixed doesn't mean that it is actually fixed. Yep.
What's the difference of
unsigned versus signed?
Unsigned, long.
Not really much in this case. When you're doing left shifting, it doesn't really matter. When you're doing right shifting, then it does matter. Because when you're doing right shifting, a signed number has what we call sign extension. So it will replicate bit 63 if it is a signed number. If it is an unsigned, it will just pad it with zeros. But in this case, it doesn't matter because we are shifting to the left. So make again, GDB main, and this time I'll just put a breakpoint on line 10 because the first two cases, is not going to be important. Single step. Now, if you don't want to, step through all of this stuff, you can just locate, the correct place to put a breakpoint, and which is right about here. Okay. Print num, print sign. I'm good. Yep.
So as you said, we can locate to our breakpoint to the place where we found.
Yep.
But it iterate 3 times, like first with a positive number, then positive number, then negative.
Right.
So how it makes sense to break that
on the third attempt?
Yes.
There are ways to do it, but it's really kind of complicated.
Okay,
so
in
what
this condition, we have to run.
Right. And this is printing it in binary, which is kind of boring. But for those of you who really want to double check and confirm everything, you should count that there are exactly 63 zeros.
I like the visual representation. It made it easier to see where it's moving along.
Yeah, I personally like this a lot better because now it's easier to count.
Easier to count, but then you have to do conversions.
Yeah, but I can do that in my head. As will you. Yep.
What the print T stand for?
Binary.
And X for hexadecimal?
Hexadecimal. So all you have to do is to print, help print, and it will tell you all the tricks you can do with print.
Where?
Yeah, the whole Linux thing is, for people who are, who read this stuff and kind of actively read into documentation. But it's terse, but everything is here. And of course, in the convention of everything open source, if another command has a full explanation, it says cx command.
How you say help X?
Then you say help x, right? Then it gives you the full explanation of what you need to know.
It's even not full screen. Can read it from the beginning according to them.
Well, you can do that later. see, well, the focus of this class is to finish the program, right?
Yes.
All right, so what we have done so far is parsing the first digit. I am all the way here now. Well, I mean, the rest is not much different, okay? It really is the same thing. Something is optional. Let's see if it's there, okay? That's basically the bottom line, okay? So what I can expect here is I can expect a period for a decimal point, or I can expect an exponent right away, or something else, okay, which is the null terminator. So I have to look for these two things, a period, a decimal point, or lowercase e. Okay. So I would look for a period first because that has to appear before the exponent. So now I say, if whatever PTR points to is a period, then I have something to process. And what I have to process here, and it really helps to write comments because I would lose track of my own program if I did not leave comments here, okay? So this is process decimal point, okay? So if I confirm this is already a decimal point, I can just go ahead and move forward because there really is nothing else that I really should do at this point other than, okay, let's see what is next, okay? And what is next can be any number of digits, or I can go straight to the exponent. So what I will do is I will do the same thing as last time. In other words, I'm going to use a counter to remember how many characters are processed, and I would also use result to remember, if I do process a decimal number, what is the value of that decimal number. So I say counter equals to parse dec whatever PTR points to, okay, which is the rest of the string, and the address of result. Okay, so I'm attempting to see if there's a decimal number after the decimal point. Okay, if there is, then I have something to do. Otherwise, I really don't have anything to do at this point. Okay, so if counter is non-zero, I'm gonna get into the conditional statement starting on line 73, and then I will say, oh, okay, so there are digits after the decimal point after all. So this is the magic. This is where you have to do something about the numerator, okay? And also the decimal exponent. So since I know that I have to deal with a decimal exponent, I'm going to create that local variable, but I have to remember where to come back next. So in VI, I can do an m, lowercase m, and lowercase a to set a bookmark here. Then I can go back and then I can jump back to this point later on. So now I can say integer decimal exponent, which by default is 0. And then I can do a backtick, which is the back quote at the upper left corner of the keyboard, and lowercase a to jump back to the bookmark that I have set earlier.
Okay, so I had to watch video.
So for those of you who play Portal, you know what this is for, right? Okay.
Through the hole.
Yep, you just shoot the portal gun. I mean, yep. So, all right. So now that we have that variable, we can now say, okay, whatever counter is, I need to multiply the first number, which is in numerator at this point, by 10 to the power of counter. That's what I need to do. Okay. But I don't have a power function, and I'm not supposed to use the actual real power function. So what I'll do is I'm going to write my own, right? Roll my own when it's not there. Okay. So we say, I can use unsigned in this case here because we know all of these will be unsigned numbers. Yep, go ahead.
Is it okay to write our code on the bottom and prototype on the top?
Say again?
Is it okay to write our
you have
program on the
to
bottom and prototype?
expose the prototype in order to use it. So you have to do something else to do. Okay, so I'm gonna do unsigned result is 1, and we say while x minus result plus equal to 10, return result, and I'm done. So this is just for calculating 10 to the power of x, and x can be 0. Okay. So now we do a backtick a, getting back to this point, and we can say the numerator is multiplying to power 10 counter here. But we also have to remember that we have to adjust for that, right? We have to adjust for it. So the denominator has to be the same amount. Does that make any sense? Because we want to preserve the value that we are dealing with. So if I multiply the numerator by a certain number in order to preserve the value of numerator divided by denominator, the denominator will have to be multiplied by the same amount. Is that okay? So that means I need a variable called denominator. So let me jump back to the point where local variables are defined in 64 underscore t. This one doesn't have to be 64-bit. We'll just no, it does. Okay, so we have to do it this way. And we talked about this in class. It's best to use unsigned integer, okay, because when you do the division, that's when things can potentially go wrong. Okay, so we can jump back to this point. Oh, wait. R. Okay. This one should be a 1. By default, it is 1, and we are now changing it to a certain power of 10. Are we still doing okay so far with all this stuff? Okay. All right, so when this is all done, we will move forward. Okay, so I have processed a single period, and any potential characters after that, I just have to remember to increment the counter by the number of characters that I have processed. Okay, because otherwise it will keep processing those digits again and again. Okay, so at this point I'm done with the decimal point. I'm done with the digits after the decimal point. I'm now at the point where the exponent can appear. Okay, so now I can say if PTR points to a e, lowercase e, then I got something else to process. Okay, all right. So the first thing is I will need counter at some point. Okay, and I'll need result at some point. So I'm going to do the same local variables here, plus PTR, and leave myself some comments. Okay, process base 10 exponent. All right. After the E, I can expect a sign, kind of like before. So if you kind of want to structure your code right, you can write the subroutine to deal with the sign and the digits after that. Okay, but I'm not doing that. So now we can say if PTR is negative, and we'll do something else. If it is positive, we'll do something, and then we'll do, there's no error checking here. Okay, the error checking doesn't apply here. I'm changing the logic flow a little bit in this case. Okay. So if it is a negative sign, the first thing we do is let's get past this point, but I have to remember the exponent in base 10 is a negative number now. Okay, so I have to somehow indicate that. Go ahead and say sign of decimal exponent, okay, and we'll just remember that. Sign of decimal exponent is -1 in this case, and by default it is just a +1. If I process a plus sign, there's nothing to do, I just have to move on to the next one. So at this point I would have processed an optional sign. If a sign is not there, I simply would not have done anything. So now I should expect digits, at least one, possibly multiple. So now I can say counter equals to parse decimal PTR and the address of result. So I'm actually processing the magnitude of the exponent in base 10 at this point. Okay, counter should be non-zero. If it is 0, it's time to report an error. But since I did not ask you to check for errors, it's okay. So what we need to do now, the counter is not even important in this case because it is actually just the result that I need. So now I can say, okay, put a marker here again, and go back to the beginning and see if I have that already defined. Nope, I don't. So I'm gonna put it here. So and this is the decimal exponent, which will be useful later. Or do I need to put it here? Nah, I don't really need it here. Okay, I can just put it here to do the processing. All right, so I'm opening a new local scope, just so that the local variables here are not exposed anywhere else. I'm not sure how many people do that. Do you guys do something like this? Like just define a block so that you can define some local variables, so that those local variables would not be exposed to the rest of the program.
Sometimes.
No, you don't? Okay. I personally find it useful, okay, in my type of programming. Okay, so at this point, we should have everything that we need to come up with the numerator and also the denominator. So what I will do is to check whether it's positive or negative, and which way it goes. And this result should have a default of 0. So I'm assuming the exponent has a 0. So if there's no e, well, it has to be something at this point. So I'm gonna say result is sign of decimal exponent multiplied to result. So this way it is either positive or negative. And depending on whether it's positive or negative, I will have to adjust either the denominator or the numerator. Okay, so now we can say while result is greater than 0, assuming it is greater than 0, we'll do the following. If it is greater than 0, then we want to increase or multiply the numerator by 10 for each count of the exponent. Is that okay? Sort of? Okay. And then we can just say minus result, because that exponent is now taken care of. While result is less than 0, we'll do the opposite. We'll multiply the denominator by 10 for each count of result, plus result in this case. And so at this point we would have adjusted for the actual exponent. And the numerator and the denominator should now reflect the correct value at this point. So I claim. Okay, time to check it, right? Okay, so let's go ahead and save the program, and just check it. GDB main. Oh, actually, I want to change main so that it includes exponent here. So we'll go ahead and try a more complex number like 7.2 times 10 to the power of, say, plus 2, and then we have plus 6.32. I mean, I'm just picking some values here. So we'll 6.25 times 10 to the power of negative 1. Okay, so this is the same as 0.625, and the last one will just specify E5. Okay, so this one is negative 50,000 as a value, negative 500,000. Sorry. Okay. So we'll test each one of these test cases and make sure the numerator and the denominator are correct at the end of ATOF. Are we still doing okay? Because I just felt kind of strange always just talking to myself. I do that when I'm actually writing programs, but usually without actually talking out loud. It would just be voices in my head.
They say you're supposed to do that. I've heard that you're supposed to debug, talk to a rubber duck.
A rubber duck?
Talking through your code, and it helps you get through it.
Because when you verbalize, I guess it exercises a certain portion of your brain where the logic part is also there. So that actually makes sense because it's all symbolic, right?
Yeah.
Yep. Right. That's good. I like it. Okay. All right, that's GDB main. And we'll put a breakpoint at the end of ATOF in this case. So this is when it is really handy to be able to open up a different terminal and just have this one fixed on the source code itself. Actually, it's ATOF that I'm interested in. And just say put a breakpoint on line 22. I'm feeling brave. I'm not sure about you, but I'm feeling kind of brave today. So I'll put a breakpoint on line ATOF.c, so you can name the file first, and then you can locate the line which is 122. So this will put a breakpoint on line 22 of the file ATOF.c, which is really handy because now you don't have to switch or wait until you're in the subroutine to do something.
So it gave us before 122, it's mean 121.
It will stop right before 122 executes, so we'll catch it right in time. Okay, so we'll run, and hopefully, yep, okay, the program didn't crash, didn't get into an infinite loop, so here, we're at least good that way. The number is not 2, okay, that's just the left over, because we did increment the pointer. And we'll go ahead and print the numerator, we'll print the denominator. So, that doesn't seem right to me, because it is 7.2. Oh, I forgot one thing. I processed all the digits after, but I did not add the value of those things to the numerator. So, okay, I caught myself. See, it is useful to stop, check before you move on. I learned that from my own mistakes. All right. So it has to do with the decimal point. After we process the decimal point, I did not I did not add basically result to the numerator, because this part shifts the first digit to the left in base 10 by counter number times. But I have to remember to add result, which is the value of the number to the right hand side of the decimal point. So that's what I missed, and that's why it did not work. Okay. All right. So we'll save it, and there's also a 2, and that 2 is, I think that 2 is correct. Okay. So let's go ahead and save it. Make GDB again. We'll put a breakpoint to ATOF.c line 22. Run the program again. Print the numerator, this time 8400. And the denominator is 10. So I added the wrong value. The value that I'm adding is incorrect.
But 7,000.
Okay, so let's check back to, oh, I used both terminals for debugging this time. So. Okay, it's supposed to be 7.2, and now it is 8400.
You change one of the 2's, so they're not, so you know which one you're looking at.
Right. Okay, so now is a good time to put a breakpoint on line 76, where the decimal point is being processed. Okay, line 76. So I will leave this one in the debug session without changing the program. Put a breakpoint on line ATOF.c line
76.
What again?
76.
76. There we go. Run the program from the beginning point again. Now we are processing the decimal point. It is a decimal point. Increase it, and then parse the digits afterwards. And I will do a next here because I know parse deck is working. But after that, I'm going to check counter. Okay, it did process only one digit, and I'll check with result should be a 2, which is this is all correct so far. Single step.
That line is wrong.
Which one?
That one. plus result. From the power 10 encounter plus result.
That is correct. Okay, so I should not be using the short form of multiplication equal to. Good catch. Good job. There we go. Or I can separate it into two lines. There we go. Okay, very good. So we got that, and I think that is accountable to both problems. Yep. All right, so let's go ahead. Make sure the file is saved on this side, and then on this side we can just do a make gdb main again, and we'll put a breakpoint on the same line, atof.c colon
122.
122. Run the program, print the numerator 7200, print the denominator, oops, den, and it's 10. So the value that we are dealing with is 720. Is that the case? Yep, 720 is the correct value. All right. Let's check the other test cases. Continue execution. And this is the second number. Print the numerator, print the denominator. And that is correct. Okay, 625 divided by 1000 is 0.625, which is 6.25 times 10 to the power of -1. So we are good there too. Continue execution. This is the last one. The numerator, the denominator, oops, keep just typing it. It's 500,000, and I think that is correct as well. Okay, so now we got the parsing part done. We have broken up everything into the numerator and the denominator, and now we can apply the rest of the logic that we talked about on Tuesday. Okay. All right. Are there any questions? Please ask some questions. I'm sick and tired of talking to myself. No? Okay. Fine.
You haven't saved the file recently.
Hmm?
You haven't saved the file recently.
Which one? ATOF?
Yep.
Yeah, I did.
Oh, you did?
Yep.
Okay.
Yep.
What if it crashes?
Which
That's all your
command
work.
is
Colon
saved?
W.
Huh?
Colon W.
You can tell because if I have made any changes, there's no sign that it has not been saved.
Is
On
it
the file name, it
Why?
changed.
Right.
Actually, Control G can tell. I think if you change it and do a Control G, it will say modified.
Right, up on the tab
Mhm.
of the file name, there's a plus when you change.
Oh,
the
okay,
fixed
right.
modification.
Yep, that as well. Yep. Okay, so now we are ready to do the actual processing of the numerator and the denominator. If I were to actually do this the right way, I would have separated this part into a different subroutine just to contain that logic. But I'm gonna, I would try to do it within the amount of time that we have, which is about 20 more minutes. Okay, so I'm thinking that I probably can do it. Okay, I can always come back and clean it up later, which is typically famous last words to actually doing any work like that. Okay, but we do have the numerator and the denominator. So the first thing we need to do is to push the numerator all the way to bit 63 and shrink the denominator until it has no zeros in the least significant portion. Okay, so those are the things that we need to do. And they sound like a lot of stuff to do. They are actually not. Okay, it's not the case. So I'm going to put a breakpoint here, MA, put a breakpoint here, and go back here because I need an integer to keep track of the exponent in base 2. So I will have exponent in base 2, and that will start with a 0. So this is before we make any adjustments. And now I can go back to here where we left off using the backtick and A. You can set 26 local bookmarks and 26 what we call global bookmarks. A global bookmark allows you to jump across files, which is kind of handy. Okay, anyway, so now we are back to this point, and it is time to make the numerator as big as possible. Okay, so the way to do that is to put it in a while loop and say while the numerator and unsigned. You know what? I'm a little bit sick and tired of having to do typecasting to just one itself because I will keep forgetting to do it. So I'm gonna do a pound define here and say big one is unsigned integer 64-bit underscore t1, and we'll use extra parentheses just to be sure. Okay, so now I can say big one shifted 63 times to the left hand side, and as long as this bit is not a 1, we'll keep shifting. Oops, gotta do the assignment here, otherwise it's a useless operator. And then we have to remember to adjust the exponent. This is going to increase or double the value of the numerator. So in order to cancel out this effect, we have to subtract 1 from the exponent of in base 2. So I have to do this for the exponent. Are we still doing okay so far with this? Okay. All right. So that would take care of the numerator, and now we have to take care of the denominator. So the denominator is something similar, but it's actually simpler. Because in this case, we are basically just saying if the least significant bit of the denominator is a 0, shift it out. And when we shift out a bit in the denominator, we are decreasing, we're halving the value of the denominator, which is doubling the actual value. So we have to compensate by also subtracting 1 from the exponent of 2. Are we still doing okay so far with this? Any questions? No? Okay, go ahead.
I'm not sure why we do the number shifts to a 63. So
that's a bit mask. Let me make it clear, how the parentheses work. So this is with extra parentheses. So big one left shift 63 is basically just 1 followed by 63 zeros. So I'm doing a bitwise AND with that to see if that bit is a 0 or a 1. That okay? Okay, it's time to double check again, right? Okay, this is line 123, so let's save the file. Do the make on this side. Yep.
in our class we go over an example. At that time we shift the 62 bits.
62. Well, that's a particular example. That's 3 itself. It's not using a loop. But when you use a loop, this is generalized. It will work on any number. The example in the class, because 3 is using up 2 bits already, and that's why it only has to shift 62 times to make the most significant bit a 1.
So if our number is bigger than 2 or 3, so loop stop before that? So if our number is bigger than, here we use a 3 as example, so it take a place of 2 bits.
Yeah.
So if it's more than that, so loop end on that place.
Because 62 left shift operations would fill bit 63 already, so that's why in the example I only use 62. But in this case, it's a loop to keep shifting until that bit is a 1. Yep. Okay, so let's go ahead and just list this code here, because I don't want to have to go through the loop completely. So we'll put a breakpoint on line 33, just continue execution, the whole thing, and we'll print the numerator. Looks pretty good, but I cannot really be sure, right? So I can now say print num ampersand unsigned long 1 shifted 63 times, and it is a non-zero. So we are good. Okay, we accomplished what we are supposed to do.
So we don't know what's running there. They
Mhm.
didn't show the negative should be 1.
Okay, say again.
If that bit is negative, should be 1.
Okay.
The running final.
All right, just hold on a second. This is what we can do also. Print double num divided by double denominator times, I guess power may not be here, so I have to be sure about that. This is the exponent 2. Yeah, can't do that. Let's see, does it take that? No, it has a different meaning. It means multiply the content pointed to by exp. So I can't really quite do what I want to explain here. So that's you just kind of have to take my words for it at this point. But when I look at the denominator, it is right because there's a 1 at the least significant bit. So I'm pretty sure that the numerator and the denominator are now correct. Okay, and I just want to also take a look at the exponent, which is negative 52. Looks about right to me because it's the number of bits that we have to shift to the left with the numerator and the number of bits that we have to shift to the right with the denominator. That's about right. Sounds right to me. So I think this is working. So we'll go ahead and continue because I do want to finish this program in about 10 minutes. And I think we'll be able to do it. All right, so now that we have the numerator, the denominator, and everything in the right place, we'll go ahead and do the actual division, right? So now we'll say num / equal to den, okay, to get the quotient back into num, okay? And then we want to shift num in either way so that it is using bit 51, okay? But none of the more significant bits, okay? So now we can say while num is less than big num or big 1 left shifted 52 times, okay? If we are not there yet. Sorry?
I keep reading that as bygone.
Bygone, yeah. Well. That's your brain, your mind filling in the gaps based on what else you're thinking. Okay, so we'll do a left shift by 1 so that we are gradually getting closer to what we want. But when we are doubling the value of the number represented this way, we have to also subtract 1 from the 2's exponent to compensate for that. And then the other one is while num is greater than or equal to bygone shifted 53 times, okay? Because we don't want that bit to be a 1, okay? So if I have a number that is greater than or equal to this particular value, we have to have it. We have to keep shifting to the other side until it is there. But in this case, because we are having the value of the quotient, we have to double the exponent to make up for that. Okay, so when this is all done, bit 52 should be a 1 and all the more significant bits should be zeros. Okay. All right. So now we have everything adjusted, and then one last adjustment is to the exponent itself, because we have to shift the binary point all the way from the default position to the left. But every time we shift one position to the left, we have to add 1 to the exponent. So that means we have to say exp plus equal to 52 just to compensate for that. And then we have to get rid of bit 52 itself, which means the quotient needs to be, we just need to get rid of that bit. And assuming that bit is always a 1 already at this point, which it should be, we can just do exclusive OR with big one left shifted 52 times. And when this is all done, we actually have everything now. So the exponent needs to be offset by 1023. So we'll add 1023 to it. And we have all the components at this point. So what is left to do is just to combine everything. So when we combine everything, that means x. Okay, x is a unsigned 64-bit integer, which is okay. You know, it got all the way out. Okay. So that means x is going to be the sign itself, bitwise OR, with the exponent, which is now a 11-bit thing, and that has to be shifted 52 times to the left, and what is left in num is the fraction. So we should be done at this point. We don't know yet, okay? We got to test it. So we'll go ahead and go back to main.c, and that should be enough to test it, because I can use the union and print out the floating point interpretation of the bit pattern, and that should do it. So now we are ready to remake the program, and I just like to use GDB for this purpose. So we'll GDB the whole thing and put a breakpoint on line 8 of the main program. I'm not even going to bother to trace into ATOF unless it is wrong. Okay, then we'll go back and trace it. So we'll run the program. Do a next so that we are not tracing into the subroutine. It will stop on line 9, and here's the moment of truth. Can I handle the truth?
Yes. No.
And it is not right.
The negative 309 looks a little familiar.
Okay, so that means I have to go back into the program and do some debugging. Okay, so atof.c, let's see where would be a good point. Pretty sure it's still working at this point on line 33, so I'll just be brave and stop on line 44. Okay, we'll skip all the loops, because I think the loops are still working correctly. Okay, so we'll go ahead and put a breakpoint on atof.c line 144. Run the program from scratch, go do the whole thing, continue execution. Okay, now we can check. So print num. Okay, this is after all the shifting. So the first thing I would need to check is bit 52 set in this case. So I'm going to say print num. I can do it this way too. Okay, so I can shift it to the right hand side 51 times, and it is a 2. Okay, that's right. Okay, so if I shift it 52 times, it is a 1. So that means bit 52 in fact is a 1. Okay, so the quotient is done correctly. Let's check exponent. It is negative 43, which sounds correct to me. All right. So now we are in the loop. This is what we are going to do now. We are basically correcting for the number itself. We are on line 144. This is where we are. So we are going to increase the exponent by 52, because those are the implicit shifts of the binary number. Single step, that should not be a big deal. We are shifting. We're removing bit 52 in this case, and that should be okay too. So let me just check. So num shifted 52 times should be a 0, and that is correct. We are increasing exponent by 1023, so everything is okay at this point. It is only, oh yeah, okay, I know why. I forgot to cast EXP. It's a 32-bit number. If I shift it 52 times, it becomes a 0. That's it. Okay, fine. We still got 3 minutes to go. U and 64 underscore T. There we go. Okay, that should fix it. Okay, GDB main. Put a breakpoint on line 8. Run the program. Next, print u.f. Yay!
Yay.
Next, print u.f. Yay! Next, print u.f. Yay! Even the sign is taken care of, so I'm fairly confident it's working. Okay. Yay! So now I can just go ahead and continue the rest of the program. It prints U is 1023, V is 0.1253, and the multiplication gives you 128 something. That sounds correct to me.
That's one result. Yeah.
Okay. And with a minute and 20 seconds to spare.
If you wrote that long program and our answer is still 0, 0, so everything is so
I'll have
partial
to
credit. So
partial credit. I will have to feed it different test cases, so maybe it will work for some test cases. Now, just for your reference, as when I was in college, I enjoyed speed programming. They have. I went to San Francisco State University, and they organize programming contests, where you would go into a computer lab with with a whole bunch of people who want to kind of play that too, and then a professor would make up some questions, according to what is expected from a like a junior or a senior year student. So typically it would involve something like parsing. One question that I got was, these are the phonemes, okay, and the program is supposed to do the phonics thing and break words into individual phonics parts, okay, and that's what the program is supposed to do. Another program is supposed to print all combinations of something, okay, so you have to I cannot remember whether you can reuse a symbol or not, okay, but you have to print all possible permutations of the same chunk of digits and something along that line. So you'll be given about 5 problems of this kind of magnitude, typically something that you would not have seen before in a programming class, so you have to basically start thinking about the solution while you are over there. They will pick the winner based on who gets to finish all programs, okay, and pass all the test cases. If no one can do that, then they will judge based on who can finish the most programs in terms of numbers. And it was fun. I actually participated in both years when I was in San Francisco State University, when I was a freshman and sophomore. The first time they didn't give me anything because they said, you're a freshman, you're not qualified. The second year I was a sophomore, so they gave me a nice XP calculator.
okay.
Find a programmer job you will do a lot.
Well,
Yes,
I got a job as a developer for a while. That's what I did, for 8 years before I got this job.
Where?
It's a company in Davis called Z-World at the time. Now it's called Rabbit Semiconductor. And my job was to help maintain everything software. So I was in charge of the compiler, the GUI of the compiler, the assembler, the firmware code, the library code, sample code that we distribute to customers, and then the tech editor decided that I will also be in charge of writing user manuals.
Coding every.
And then later on, I also helped develop help debug hardware, because I was kind of sick and tired of having to work on, because they design single board computers, or SBCs, which are by today's standard is a dinosaur, is like obsolete completely. But it's a single board computer which has no debugging capability whatsoever. And this is back in the good old days where ROM is like a chip with a little glass window on it. So to erase it, you have to pull the chip off, put it under intense UV light for 15 minutes in order to erase it. None of that flash memory nonsense that we have today. Okay, it's like, 15 seconds, it's all reprogrammed. No, you pull it out using a little tweezer thing and make sure you don't bend the pins. Put it into the eraser thing for 15 minutes, and then take it back out, and you can reprogram it using a dedicated EEPROM programmer that connects to the parallel port of a computer. So there's no GDB that can run on the target platform. Okay, that much you can know for sure. The only indicator that you might be able to use to see if your code gets to a certain point is a bunch of LEDs. When I say a bunch, usually it's just two. Oh, that LED turned on. I at least got to a certain point of the program. And sometimes your program would not work at all because you're getting a prototype board and the hardware engineer, the guy who designed the PCB, made a mistake with the logic gates. So it would not address the memory correctly, it won't exercise the chip select line, or the address bus is not hooked up correctly. And then when I take it back to the guy who designed the circuit board, they always blame it on software. It's like, Tech, you just don't know how to write software. that's why it's not working.
Okay, say this. Every time you claim that, you build up a tab of $1,000, and you have to prove that you are wrong. I catch it.
Yeah, so I started to develop the ability to read schematics just so that I can prove them wrong. And that's how I got into this whole thing, in assembly, programming, the schematic stuff, and all kinds of stuff like that. It's all fun. And at the same time, I was in graduate school, basically full-time student, part-time, doing that. Yep.
What would happen to the company if for some reason you were not able to work for them anymore on the spot?
I would imagine something undesirable because I was the only software engineer at the time. I
can't come anymore. We're doomed.
They would probably kidnap me or something. When I joined the company, they only had 12 people. When I left the company, they had about 120. And we eventually had 9 people doing software because I was one of 9. Actually, no, I take it back. I was one of 7, so there were 7 of us when I left. Yeah, we used Borg designation. That's interesting because that's how we actually functioned.